Thank you very much. Good morning. Thank you very much for your invitation for this opportunity to give this speech at this electronics conference. My name is José Carrasco. I come from a small company in Spain, and our main activity is to design and manufacture electronics for space systems. We are a company very small. We are only 10 people. But we have a laboratory equipped with different instrumentation to make the design of equipment that has flown already and that will fly in the future. We have a small clean room, several contacts with the European Space Agency, and some other contacts with other companies. We have developed as well a platform, a small platform, a CubeSat type platform for doing experiments in space that we offer as a closed product, so that any scientist that wants to realize an experiment in space doesn't have to worry about how everything works and how it has to be launched. Has to prepare only his experiment or her experiment, put it in the platform, and we can fly for him or for her. So we have one mission plan already, and as we have this small platform, we were selected for an European Space Agency project to participate in a mission to an asteroid. So this is what I'm going to describe in this conference. The outline of this conference is to outline the differences between a platform or a small platform that is orbiting around Earth and one that goes beyond the orbit of the Earth. Then I will describe, as an example, a deep space scenario that we participated in, and I will describe a proposed small platform that may go outside Earth orbit, and then the topology of the platform, for the mission. In particular, how the electronics has been tailored for fulfilling this mission. So the scenario that I'm going to describe is a mission that is being planned by NASA and the European Space Agency to visit an asteroid and to try to divert the orbit of it by impacting a probe that will travel from Earth directly to impact on the asteroid. This is part of the NASA mission. NASA will launch a probe that will travel on its own to impact on the asteroid. And on its own, ESA will launch a probe that will be orbiting the asteroid where the impactor comes and crashes on the asteroid. As part of the mission, so this is the impactor, and this is ESA's probe. The name of the asteroid is Didymus. I will describe it later. It's a binary asteroid. And as part of the mission, of the ESA mission, the probe from ESA will have two CubeSat and a lander as well. So when the ESA spacecraft reaches the orbit of the asteroid, it will keep orbiting, and it will release one lander that will land on the asteroid, and two CubeSats that one of them will orbit around and the other one will orbit will actually orbit the asteroid. So this is an image of the ESA probe orbiting the asteroid. The asteroid is double, as I mentioned, the two CubeSats, and the expected scenario when the impactor comes and impacts on the asteroid. So what we want to do when we arrive into the asteroid is to study the basic properties of the asteroid. And the basic properties are: what's the gravity of the body, does it have a magnetic field or not, and what are the properties of the soil? Is it solid or how it's covered? How is the regolith that covers the asteroid? Does it have a solid surface, or will the landers that go to the asteroid just bury deep inside the asteroid because the surface is not solid? So this is the part of the science that the ESA probe is going to do, the lander and the CubeSat. And of course, there are many players in the mission. From the point of view of the industries involved, our eye is kept in the possibilities of getting information for future mining, space mining of asteroids. This is what we have in mind as a company. Okay, this is what we know. Practically, what we know about the asteroid is just a few things, just guess estimations on how it behaves. This is the only image that we have, which is gotten using a radar from the Earth. And what we imagine is that the asteroid has this shape. It's a little bit elongating on its equator. This is the equator. It's binary. It has a moon orbiting around. And the plan is to actually land on the moon and on the real asteroid. Because if the assumptions are correct, the gravity of the asteroid is very, very, very low. The escape speed is just 6 centimeters per second. So if you have a very, very small speed, you will not, it's very difficult to land on it. And even it is supposed that over the equator of the main body, the escape velocity is equal to the velocity of its rotation. So in fact, any stone or any dust sitting on the equator is actually escaping out of the asteroid. So it's very difficult to land on it. If any possibility to land on the main asteroid should be in the poles, and so this is avoided, and the mission will land on the actual moon of the asteroid. So going to the even if the plan for our platform is to land on the asteroid just to being released. It's a very small satellites, CubeSat type. It doesn't have any propulsion, nothing. So if we are just released and trust on the gravity of the asteroid, there is some possibilities that we actually end up landing there. Although the possibilities are not 100%, because even being released at a very, very small speed, the CubeSat, the released CubeSat, will impact on the surface, will rebound several times, and there is some possibilities that after rebounding up to 34 times, there is some possibilities that it will actually be on the surface, or there are even some possibilities that it will go up, it will go out of the orbit of the asteroid. So if we end up in the surface, we'll have to cope with the extreme environment that is around the asteroid. From the thermal point of view, and this is a thermal modeling of the asteroid, just a model of what we suppose is to be the thermal environment around the asteroid. If you think of the Earth is actually a very balmy environment around. The Earth keeps heating up the bodies orbiting it, even when they are under eclipse, because the Earth radiation, even on the dark side, is very, very high. So it's very easy for a satellite to keep its temperature more or less constant when orbiting the Earth. But for a body that is outside, for a small body that is at 1 or 1 point something astronomical units of the sun, and for this particular, and this is true for any deep space experiment, the temperature, this is a model of the temperature when a satellite orbiting the asteroid is being under sun illumination, its temperature may go up to 320 Kelvin, so plus 40 degrees or something like that. And if it goes under the asteroid, if it's under dark, the temperature may go down to less than 200 K, so minus 80 degrees or even less than that. So it's not that easy to keep the electronics working under that extreme environment. And even if you try to follow the strategy that is followed within the ESA orbit, which is just painting the satellite with coating, where you can control the emissiveness of the satellite. If you paint it with black paint, for instance, you may get a very good temperature, 11 degrees when under the sun, but minus 130 degrees under eclipse. And if you paint it with aluminized Kapton that has very low emissivity, when you are under eclipse, it's minus 34 degrees, which is okay for the electronics. But when you get in sunlight, you go up to 100 degrees centigrade. So this is not quite good for the electronics point of view. Even for the electronics, normal electronics that you know it works from storage minus 65 to 150. Normal work nominal temperature is minus 42 plus 85. If, of course, it's possible to get the electronics working outside these limits, even for very low temperatures, it's possible to qualify normal electronics for going down cryogenic temperature minus 200 something degrees, because you have to provide special mounting techniques to avoid the stress that the electronics suffer when going in a thermal cycle. This is a normal way of mounting the components when they are going to work in a very extreme environment to have a stress relief in the lids of the PCBs, for instance. And it's not seen very well, but I have a picture here on how a DC-DC converter, a power converter, may be qualified in a case-by-case basis. A normal DC-DC converter that works within this temperature range may be qualified down to 200 degrees Kelvin, to minus 100 degrees below zero, because in fact the MOSFET transistors work better at low temperatures, but the real effect of all the components may be beneficial for any range of powers and maybe very bad for another range. So it could be done, but in our approach we haven't followed that approach, and what we have decided to make the electronics work in these extreme temperatures is to cover, this is the exterior part of the satellite, the inner part of the satellite, and in the middle we have put a multi-layer insulation that keeps a very good insulation between the outside and the inside, and has a very low thermal conductivity between the inside and the outside. Of course, this multi-layer insulation, if we have something releasing power in here, the temperature inside can go very high, and that's why we have a thermal switch that connects the internal part and the external part of the structure. So if the exterior is at low temperature and the interior is high temperature, we may connect both sides and evacuate heat. And if the interior is at low temperature and the exterior is at a high temperature, we may connect as well the inner and outer side and get heat inside the satellite. So we have a temperature regulation with this thermal switch, and we have a layer insulation, the multi-layer insulation, to try to keep the electronics between minus 14 plus 85 degrees centigrade. Of course, we have to make sure that this structure, from the point of view of a launch, will withstand, and that means to have AM frequencies as high as possible, and to ensure a launch having AM frequencies bigger than 200 Hz. That's guaranteed when the satellite is supported on the edges or on the sides. So we may, with this structure, we need some simulations to guarantee that. And for the thermal point of view, we've made some simulations of the satellite as well to see what's the temperature inside and what's the temperature outside when the CubeSat is deployed and when it's resting on the surface of the asteroid. And as you may see, when these are to thermal, the working of the thermal control of the satellite, this is the actual temperature outside, the blue line, and this is the temperature of the satellite when of the interior of the satellite with two loads working. If we have too much load in the interior of the satellite, the temperature inside goes up, and if we have no load, or a very small load, very small power being consumed inside the satellite, the temperature is kept low. And this is while descending, this is while on the surface, and this is in the surface with no load. This is in the surface with no power consumed inside. And what we have seen is if the thermal switch is kept on, we have this kind of power profile. If we play with thermal switch, and when the exterior is warm, we switch on the thermal switch, we heat up the exterior of the satellite, and when the internal part, when the exterior is at low temperatures, we switch off the thermal switch, we don't get the internal temperature going down. We may regulate the temperature inside the satellite to be kept at bigger than minus 40 degrees at lower temperatures than plus 85. This is the electrical block diagram of the platform as well. As we have seen before, we have the faces of the satellite do not have the same number of solar cells in each of them because we need to have communications antenna with the main platform to relay the data that we get, and therefore we have an asymmetrical solar panels, and for that we have designed a power system that extracts the maximum power of each face of the satellite and not of the combination of what is happening at each side. So we get, even if the solar panels are different, even if they are unevenly illuminated, we may get the maximum power of each of the faces of the satellite. Then we have some protection of each line to avoid the batteries being discharged under the solar panels that is not under illumination. And we rely on two batteries, one primary battery and a secondary battery. The secondary battery will be recharged by the solar panels, and the primary battery is not recharged, it's not rechargeable. And this is because if we land in a dark area, we at least rely on a primary battery that guarantees a minimum science for emission. And if we end up landing in an illuminated area, we've got a secondary battery that may be charged and discharged using the solar arrays, and will be discharged to the payloads through a power distribution unit. We have power distribution unit fully protected with over voltage and over current, and with protection, or if there is a low latch due to the passage of an alpha particle, something happens, what is called a single event offset or a single event launch. We may react up on that, and open the load and reset a load that is malfunctioning. Payloads are here with the science. We've got the radio of the antennas and a heater that helps the thermal switch to keep the temperature of the inside of the satellite regulated. This is a view of the solar regulators, which are quite small. In fact, we've got here 8 solar regulators in the footprint of a CubeSat. For this mission, we only need 4, but it's just a picture to show you that they are, even if they have maximum power points tracking of the solar arrays, the electronics is quite small. And this is why we are not using any kind of power or microprocessor or anything like that to calculate the maximum power point. Maximum power point is calculated using a very, very simple technique which consists on multiplying the current and the voltage across the solar array using the same power width modulation technique that is being using that regulate the output current from the solar array and charging the battery. If we make a multiplication using a PWM multiplier of the current and voltage, we soon realize that this is not the power, this is not the real power going out of the power of the solar array, but this PWM multiplication has the same maximum power point as the maximum power point of the solar array. And then using this very simple thing, it is possible to get the maximum power from the solar array. This is what we got. And for instance, for this main mission, this is the power profile of the mission, the power being extracted from the batteries. We consider the satellite is always under illumination, and the actual charge of the battery that is going down and up, and is being recharged after an eclipse period. So we may end up working in this mode for practically forever. And this is the working of the heater that, in combination with the thermal switch, is regulating the temperature inside the satellite. Of course, we are providing some, just as an example, some protections for single-level latching, single-level upsets of the payload going outside. Everything is protected and redundant. As an example, I've got here the redundancy implemented in a very simple linear power supply. This is a linear power supply that is composed by the transistor regulator, whose output voltage is being regulated by a zener. But as we want anything in here to fail and the power supply continue working, everything is duplicated. The regulating transistor duplicated, the zener is duplicated. We have some protections to diodes, and if something here fails, we have another one duplicated as well to provide power to provide power to the system. And of course, one of the things that we have here as well is that we only have one power. The battery cells are only providing us 3.5 volts. So that's very, very small voltage. And if we want to regulate, and if we want to get 5 volts, for instance, out of 3.5 volts, we may put a boost regulator. But as the voltages are so low, and we have to use radiation-hardened electronics, there are not in the market any such components to work under radiation environments with such a small voltage explosion to work with, and that's why, for instance, the error amplifier of the boost regulator is implemented using discrete components, just to be able to withstand the radiation environment within the satellite. I've got another example of a power supply. Power supplies to extract more several 10 volts from the battery may be implemented using a very simple resonance silicon power supply implemented by a person working in the European Space Agency, and with this is a converter whose primary waveforms are resonating, and with a very simple topology we may increase the voltage given by the batteries with 99% efficiency. We need an umbilical connector as well, although this is not included in the CubeSat standard. We are using a commercial connector. Before the deployment of the CubeSat, we need to get some data of what is happening or what is going to happen, and of course we need to recharge the secondary battery because it will be discharged during the journey to the asteroid. And this is a connector that we are using. This is the connection between the main spacecraft and the CubeSat, which is a very usual circuitry. Again, duplicated. This is only one line of the RS-485 line, which as well, any component in here may fail and the line continue working. Sometimes, if one of the components fails, the line continues working, and sometimes one of the lines, if a component here fails and this line fails, we have a redundant line to continue the operation of the communication of the satellite. And this is the radio link between the satellite and the main spacecraft, which is a prototype of an engineering model of the radio link. And as well as before, in a CubeSat footprint, we have a radio working at 5.8 gigahertz with turbo codes and convolutional codes for data encoding and for communications. And this is a general view of the mission that we've been preparing for ESA for going to an asteroid. That's an example of the electronics involved in a small platform as well. Thank you very much. Thank you. if you want
I
any
think you
questions.
have some questions, yes?
I'm really curious how you stabilize the satellite, because if it is on Earth orbit, that's magnetic field that
Yeah.
will be used. But here you don't have the magnetic field.
Yeah, and in fact we don't have nothing, we don't expect to have magnetic field, and it is not stabilized. The main goal was to do the platform as simple as possible, and simplest thing is having no stabilization, no altitude control. So the CubeSat is released at much less than 6 centimeters per second, because if it's released at 6 centimeters per second, we will not land in the satellite, and it just goes down tumbling, and it lands. Of course, when releasing, you have to ensure that it doesn't go outside tumbling, because if when it touches the surface, the tumbling translates into kinetic energy, it will not stop the rebound, and it will go out of the asteroid as well. So it has to get out of the main spacecraft very gently, very smoothly, and with very small speed to actually land on the satellite. But there are in fact no qualified attitude control system for CubeSats out of the Earth environment. So,
More questions?
I'm wondering when you will collect the data, or you store it somewhere locally in these satellites,
Yeah.
or you transmit them,
Yeah.
where is the data will be stored?
Where?
Where the data
well, there is a local storage. Because
local storage? So memories?
yeah, memory, flash memory. There is flash memory qualified for space applications, but you have to provide it with single level latch protections. So if some particle goes through, sometimes the memory consumes all the power, and there is a current sensor that measures the current being actually consumed by the memory, and if the current consumption goes high, you switch off everything, reset the memory, and put into working again. So the flash memories have been used in space. So we store the data locally, and then we have some communication windows with the main spacecraft, and then that's all planned.
So, no more questions? Yes.
How long it's designed to operate out in space?
Yeah, once we are released, it's 3 months operation, so we don't have to worry very much about total dose radiation, but we have to worry about the particles, the radiation going through.
So, I see there are no more questions.
Thank you
And
very
a
much.
special gift for our presenter.
Thank you.
And now we have